right? Okay, so now let's look at what is an ensemble. For classification, the idea of an ensemble is quite simple. You have classifier 1, and you have classifier 2. Okay, and all we do is we combine their results. So how do we combine? Basically, we take the, let's say if we are looking at a binary classification problem, then we just take the mode of their decision. So mode won't work with 2, we will need to have 3. So let's say classifier 3. Okay, so basically your decision is going to be, your class is going to be, so basically y is equal to mode over m. M is the number of classifiers, m is equal to 1, 2, 3, okay, of ym of whatever is the result that you get, right? So this is going to be for the mth classifier, whatever input you give it. Okay, so I can give the index I. Okay, so it's just the mode. So we are basically taking voting over 3 classifiers, and whichever class gets 2 or 3 votes, okay, whichever gets the majority vote, that class is declared as the class that is decided by the classifier. Now, why should this work? This can only work when these classifiers are somewhat independent of each other. If all 3 classifiers are exactly the same, right, then basically if we take the mode or the voting, then it's not going to help us in any way. Okay. Or if the classifiers are adversarial to each other, whatever class 1 says class 2 is trying to sabotage it. Whatever classifier 1 is saying, classifier 2 is actively trying to sabotage it by giving the opposite decision, then it is nullifying what classifier 1 is saying. So we assume that these are we don't have either of the 2 cases. They are independent of each other. So there is an assumption of independence. Okay, that's a very strong assumption. Independence of models. Okay. It's only when the models are independent of each other that we get a strong effect of having better decisions. So now let's take an example of how these decisions can be better. Okay, so let's say we have these classes, this classifier can give you multiple different answers. So let's look at a binary classification. So the 3 different answers that we can get is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and so similarly we'll have total of 8 combinations, right? And so let's assume that we have class to be, the actual class is 1. Okay, 0, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0. Yeah, so let's look at the 8 possible combinations for binary classification. We have 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, okay, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So let's say actual class is 1. Okay, so now we want at least 2 of them to give us a probability of 1. Okay, so which ones are going to give us a correct answer? This one is going to give us correct answer, this one, and this one. Okay, these 4 are going to give us the correct answer. All right, so let's say for each classifier the probability of correct classification is p. Okay, so and the probabilities of the 3 classifiers are independent of each other. The 3 classifiers are independent of each other. So for any of these, for these 4 out of the 8 possibilities, the probability that we'll have the correct answer is going to be, so we have 1, 2 and 3 where we have two of them. So p squared 1 minus p, okay, times 3 plus p cubed. Okay. So long as p is greater than half, so long as each classifier does slightly better than chance, okay, this is going to be greater than p. If p is greater than half. Okay. And we can generalize it to any number of odd classifiers and we will get the same answer. Okay, that it will, the probability will actually, in fact, it will start with whatever is p. So this p, this is half, this is p, and it will keep increasing as we increase m, the number of classifiers. Okay, so this ensembling effect is there. Now the reason why we could multiply these, we could have p squared and p cubes and all that, is precisely because we had the independence assumption. If we did not have the independence assumption, then you cannot multiply the constituent probabilities of a joint distribution, right? So this independence assumption is there. It's a strong assumption, but it basically illustrates the point that we can combine classifiers as long as they are somewhat independent of each other. The other thing is to notice that they have to have at least some good answers. Even if p is not touching 1, it cannot be below half. Assuming balanced classes, it cannot be below half. So they have to have some learning capability, but they could be weak learners. Weak learner means that their probability of correct classification is not close to 1, but it is greater than half. Okay. So now let's look at a hypothesis class of an ensemble. If we look at simply the hypothesis class of linear classification, right? So this is your x1 and x2, and let's say we have three different ensembles, three different let's say we have three different linear classifiers in the ensemble. One is here, the other is here, the third is here. Okay, so now if we take the majority vote, it's possible that we can color some of these in such a way that we can actually have class 1 somewhere else, class 1 and somewhere else, and so forth. So we can now the average or the mode of the three classifiers, the combined classifiers, is no longer linear. Okay, it's actually a non-linear classifier. It's similar to a neural network now, with an ensemble with three linear classifiers is similar to a neural network with three hidden nodes. Okay, in some sense. So here what we are getting is we are getting an expansion of hypothesis class. Expansion over the constituent. So this is a single model. Okay, single model has this hypothesis class. Its ensemble has a bigger hypothesis class. Okay. Now let's look at the same thing for regression, just for our curiosity that ensembles really lead to better results for regression also. So let's say we have three different regressors. Okay, so we have f1 of x, f2 of x, okay, and f3 of x. Okay, and let's say they are all three linear regressors. So this is w1 xi plus b, and this is w2 xi plus b. Here w1 and w2 and w3 are all vectors. So this is b1, b2, and w3 xi transpose plus b3. These are three different classifiers. Right? So now, assuming that x is let's look at the variance of the error in this case. So let's say your target was ti. Okay, so what is the expected value of ti, right, minus yi? okay, squared. Alright, so what is this expected value? We would like this expected value to be low. We would like it to be lower, okay, and what we are saying is that your yi is going to be an average of the three. Okay, it's going to be an average of three different regressors. It could be two also, just it's an here we took an example of three. In regression we don't have to have an odd number of constituents. We can have two regressors, four regressors also. But let's look at this. So what is this expected value? So what it turns out is that this expected value is going to be we will have this sigma 1 square plus sigma 2 square, okay, plus sigma 3 square, not divided by 3 but divided by 3 square. Okay. So what that means is that the variance of the error when I take the square root is going to be 1 by square root of 3 times the variance of the average variance of the three different constituents. So what is this sigma 1? Sigma 1 is the expected value of this first one. Let's call it f1. f1 of x minus ti the whole square. Okay. And then similarly sigma 2 is the expected value of f2 of xi minus ti the whole square, and so forth. So if the three regressors give you the same variance, right, and we are taking their average, when we are taking their average, we are going to be dividing the variance by a square root of the number of the constituents. Okay. So keep that in mind. So, but this also is only true. This is only true when we have cross terms to be 0. So the reason this comes out to be like this is that if we plug in this y here and we take difference from ti the whole squared, so what we will get is we will get a yi squared term, we will get a ti squared term, and we will get ti yi terms. So whenever we have the yi squared term, in that term we will have the square of these individual terms, and we will have cross terms. Okay. So assuming everything is 0 mean, the cross terms only go 0 when the constituents are uncorrelated. So here the f1x, so we will assume that expected value of f1x, okay, the errors are going to be uncorrelated. f1x minus ti and f2x minus ti. Okay, this is 0. This is going to be 0. Only then this is possible. So they have to be uncorrelated with each other, and that uncorrelated assumption again is related to that independence assumption that we were talking about. They are not the same, but they are quite related. Only then we will get a reduction in the variance of the error. And this reduction keeps on going up as we have more and more constituents in the ensemble. Okay, let's look at a simple model of combining different classifiers. So before that, let's look at a non-parametric model for both regression and classification, where we have no parameters, we just rely on the training data, and that is a nearest neighbor model. So let's say we have the two variables x1 and x2, and we have some training points. We don't know what the target value for them is yet, but we just have some training points. Now if I take these training points and divide it into a Voronoi tessellation, what is Voronoi tessellation? I draw these lines where the line tells me which point is the closest point. So here it will be like this, here it might be like this, here it will be like so, and then it will be like that, like that, like that, right? Okay, so this is the Voronoi tessellation, and so now basically in this we have for each training point we have its zone of influence. Okay, within that zone of influence, that point is the closest training point. That's the nearest neighbor. Okay, so to speak. So now within each cell that we have, so this is called Voronoi diagram. Within each cell of the Voronoi diagram, I give it the value of Ti that is associated with that Xi. Okay, so here this is an Xi but also Ti pair. Okay, we have some training value, and that training value could be either regression value or it could be class value. For either of those, I just give that value for any X that is falling within that cell. Okay, so any test point that falls within that cell will get the same Ti value. So we will have these bunch of different levels in different cells. Okay, and that level is flat, and that level is given to that particular cell. In one dimension, it is simple to see. So let's say if we have these 3 training points, right? Whatever training value we have here, so let's say it is regression, we will have nearest neighbor here like this, and then nearest neighbor in this zone like this, and then nearest neighbor like this. So these are the bisectors between the 2 points. So these are the bisectors. So at the bisectors we will have these double sets, and that's how we have the Y versus X. Okay, so that's an example in one dimension. So that's the nearest model that we can have. That's the nearest neighbor model that we have. So here we don't have to store any parameters, we just have to compute what is the nearest training sample. So there is no parameters, it's called non-parametric model. In this non-parametric model, the downside of it is that at test time you have to compute whether a test sample is closest to training point 1, training point 2, training point 3, training point n. So you have to do n different computations, and that for a very large training data can be very cost prohibitive. The other problem is that what is the notion of nearness? Here we are looking at Euclidean distance in x1, x2 space. That may not always be the best measure of nearness. We may want to extract some features, and in that feature space we might want to operate upon Euclidean distance or cosine distance and so forth. So now, coming back to the ensembles, we can actually combine several nearest neighbor models by using some in a way that is called a K-nearest neighbor model. Okay, so here what we do is that we have the same x1, x2 space, and we have the same set of training points. Okay, so for any test point, we will find out what are the 3 nearest neighbors. And so let's say it's a 3 nearest neighbor model. It can also be 5 nearest neighbors. So this K is a hyperparameter. Okay, so we can find what are the 3 nearest neighbors, and we will take the average of the 3. So if it is regression, then the level is the average of the 3. If it is classification, then it is the voting of the 3. We will take the average decision of the 3 nearest neighbor or the 5 nearest neighbor. And what that does is, if one of the points is mislabeled, okay, or it has a noise in its target value that we recorded, then some of the other neighbors can correct for its mistakes by giving you an averaging effect. And in regression, you will see that it will smoothen out some of the boundaries, or it will make the boundaries so it will increase the number of steps that you have, because sometimes when we move in this space, which point is the nearest neighbor, that will suddenly change because now you have more neighbors to compute and so forth. So it will make the hypothesis class slightly richer, and it can have some sort of a smoothing effect and some sort of a self-correcting effect for label noise. Okay, so that's another way of combining nearest neighbor into k-nearest neighbor. And what is a good k? Whatever works best for your validation. Now back to this regression models. These ensemble models. These ensemble models work not only for linear models, they also work for ensembling neural networks, for ensembling other types of networks, other type of models such as support vector regression and support vector classification. So you can ensemble any kind of classifiers. You can even mix and match classifiers and regressors. You can take a linear regressor and ensemble it with a neural network regressor and so forth. Okay, just remember that for regression it is model averaging, for classification it is average voting, okay, or majority voting. What we can do for classification is that if the output of the classifier is probabilities as opposed to actual classes, then we can take average of probabilities also. It becomes like a regression ensemble. But what is required is that these in ensembles, that the models be somewhat independent of each other. Okay, so we'll come to how we can induce that, how we can ensure that some of these are independent of each other in a little bit. Okay,